Greetings, my inquisitive friend, and a very warm welcome to the Deepfield channel. Tonight we are going to wander through one of the most magnificent illusions the cosmos has ever woven for humanity. The notion that the world is inherently colourful, that the sky is painted blue, the grass is dyed green, and the sunset is dipped in gold. Let me share a gentle secret with you before we embark. None of this actually exists in the external world. Colour, an experience so profoundly intimate and exquisitely beautiful, resides entirely within your own mind. But I promise to keep this mystery from becoming so unsettling that it chases away your slumber. Before we plunge into this expedition, I would love to read in the comments which corner of the globe you are tuning in from tonight. And if you are feeling too drowsy to type, simply drop a brief hello. It might seem like a trivial gesture, but the tiny action signals to the platform that our space is inviting, helping us draw more weary minds here to unwind alongside us. If you enjoy our scientific voyages, please leave a like and subscribe. And to those of you who are already part of our community, my deepest gratitude. If you wish to draw even closer, consider becoming a channel member. Members receive early access to our videos before anyone else. You will find the link down in the description. Now, wherever you happen to be resting, settle into a deeply comfortable position. If sleep begins to pull you under, simply accept its invitation. Let us begin. There is an action you perform every single day, from the very second you open your eyes in the morning, yet you have likely never paused to truly question it. You gaze out at the world and perceive it bursting with hues. The golden yellow of the morning light spilling through your window, the muted green of the trees on a heavily overcast day, the striking red of a piece of fruit sitting on your table. These colours feel so natural, so undeniably obvious, so intrinsically bound to the objects that display them, that it never crosses our minds to wonder if they are truly out there, clinging to surfaces like a permanent coat of paint, or if they are actually being conjured somewhere far more private and astonishing. Colour appears to be an inherent property of objects. We state that an apple is red in the exact same way we state that it is round. We employ the same grammatical structure, as if redness and roundness belong to the exact same category of qualities, but they do not. The physical shape of an apple exists entirely independently of any eye that might observe it. If every living creature were to vanish from the cosmos tomorrow, the apple would still remain roughly spherical. But would it still be red? That is the question we will let drift down onto you tonight, as softly as a falling leaf settling onto the ground without a sound. Consider for a moment an old adage you have likely heard, that in the dark all cats are grey. There is a profound piece of folk wisdom embedded in that phrase that extends far beyond its literal meaning. In absolute darkness, devoid of any light source, colours simply vanish. They do not become hard to see, nor do they grow blurry. They literally cease to exist in that environment, and this alone should offer us a massive clue. If colour were a fixed physical property of objects like mass or density, it would not require light to exist. A stone remains heavy in the pitch black. A cube remains perfectly cubic. But a red rose in total darkness is not red at all. This initial clue leads us to realise that colour has a fundamental reliance on something external to the object itself, light. Yet, the relationship between colour and light is far more intricate than it first appears. Light in its pure form is also completely colourless. This sounds bizarre, so let us take it slowly. Light is a form of energy that travels through space as electromagnetic waves. These waves possess varying lengths, and it is these differing lengths that will eventually be interpreted as distinct colours by the brain. But the wave itself, journeying through the vacuum between the sun and your window, carries no colour tag. It is merely energy oscillating through the void, just pure motion. The physical universe at this foundational scale is remarkably devoid of hue. It is composed of particles, forces, fields, and energy, electrons orbiting atomic nuclei, photons travelling at a velocity that no other material object could ever hope to match, atoms clustering into molecules, molecules forming surfaces, surfaces that reflect and absorb energy in different ways depending on their chemical architecture. This entire cosmic machinery operates entirely without colour. There is not a single equation in all of physics that includes the variable red or blue. Such words simply do not exist in the vocabulary of the cosmos. So where do the colours we perceive actually originate? Let us build this answer gradually, because it is far more captivating than any quick summary could ever convey. It all begins with light emanating from a source, such as the sun, a light bulb, or a flickering candle. This emission is what we refer to as white light, but the term is somewhat deceptive because white light is not simple. It is in reality a complex blending of all other colours. You have likely witnessed what happens when light passes through a glass prism. It fans out to reveal a continuous band of hues, stretching from violet all the way to red. This is the visible spectrum, and what the prism is doing is separating the white light into its individual components, each possessing a slightly different wavelength. Wavelength is the measurement of a single, complete oscillation of an electromagnetic wave. Shorter waves correspond within the visible spectrum to what our brains will eventually label as violet and blue. Longer waves correspond to what our brains will label as orange and red. Green, yellow and cyan sit somewhere in the middle. The visible spectrum that human eyes are capable of detecting occupies only a minuscule sliver of the entire electromagnetic spectrum that exists. Below violet lies the ultraviolet range, followed by X-rays, and then gamma rays. Above red begins the infrared range, followed by microwaves, and then radio waves. All this vast richness of electromagnetic radiation exists, travelling across the universe, piercing through space and time, and yet we're only capable of witnessing a tiny fragment of this grand spectacle. And even that tiny fragment we do witness, we perceive in a manner entirely constructed by the brain. When light strikes an object, several different things can occur. The light might be absorbed by the material, it might be reflected, it might be transmitted straight through it, or it might be scattered. The leaf of a plant appears green to us because the pigments within it, primarily chlorophyll, predominantly absorb the shorter waves, the blues and violets, and the longer waves, the reds, while reflecting back into the environment mostly the medium-length waves, which our visual system will interpret as green. The leaf itself is not green. The leaf merely rejects certain waves and returns others. The green is born later deep inside of us. A surface that we describe as white is reflecting nearly all the waves of the visible spectrum that strike it, without preferentially absorbing any. A black surface is absorbing almost everything, returning very little back. The blackness we perceive is not the colour that the surface is emitting. It is simply the absence of enough reflection to stimulate our receptors in any meaningful way. Black in a certain sense is the silence of light. But this entire dance of absorption and reflection is still taking place in the physical realm, in the domain of waves and molecules. The colour has not yet been born. In order to be born, this reflected energy must enter an eye. The human eye is a structure of unsettling elegance. In the retina, which is the light-sensitive layer at the back of the eye, there are two primary types of receptors: the rods, which are immensely sensitive to light but do not distinguish wavelengths with precision, handling vision in low-light conditions, and the cones, which come in three distinct varieties, each more sensitive to a different band of wavelengths. One type of cone responds most vigorously to long waves, which will be associated with red. Another type responds best to medium waves, associated with green. And the third type responds most strongly to short waves, associated with blue. It is crucial to understand that these cones do not actually see colours. They are merely electrochemical receptors that fire electrical signals in response to the light energy striking them. The intensity of the signal that each type of cone sends to the brain depends on how closely the wavelength of that specific light matches its sensitivity. The long-wave cone will fire intensely if it receives light near the red end of the spectrum, and very little if it receives blue light. The short-wave cone does the exact opposite. What the eye transmits to the brain, therefore, is not a colourful picture. It is a collection of electrical signals, pulses, firing frequencies. The optic nerve carries these electrical signals up to the brain, specifically to a region at the back known as the visual cortex. And it is there, inside that dark chamber within your skull, that something truly extraordinary takes place. The brain compares the signals arriving from the 3 types of cones. It calculates the differences and similarities between these signals and, based on that computation, constructs an experience. This experience is what you refer to as colour. It is not a passive recording of the reality outside. It is an active interpretation, a creation, a narrative that the brain tells itself about the type of light that just entered the eye. Consider the analogy of a thermometer. A thermometer measures temperature. It does not feel heat in the way that you do. It registers a physical quantity and translates it into a number. Your brain does something similar with light, but in a vastly more sophisticated and subjective manner. It takes the data from the cones, compares it, processes it, and generates a qualitative experience. And that qualitative experience, that what it is like to see red, has no equivalent in the external physical world. There is a philosophical concept known as qualia, which refers precisely to this dimension of experience, the redness of red, the blue you see in the crisp sky of a summer afternoon. Not the frequency of the wave, not the angle of reflection, not the electrical signal in the optic nerve, but the lived sensation, the internal texture of the experience. Physicists can describe with extraordinary precision everything that happens right up to the moment the signal enters the brain, but what happens next, when that signal transforms into the experience of colour, remains one of the greatest mysteries in both science and philosophy. What we can state with absolute confidence is that colour is a neural construction, an interpretation, a language that the brain developed over many millions of years of evolution to help living organisms navigate their environment. The colours you see are evolutionary solutions to practical problems, distinguishing ripe fruit from unripe, spotting predators hidden in the foliage, recognising the face of an ally or a foe. And like any language, this language of colour can vary from species to species. Some animals possess only 2 types of cones, and perceive a much narrower spectrum than we do. Others possess 4, 5, or even 16 different types of cones. Mantis shrimp are famous for having a visual architecture that science is still struggling to fully comprehend. Their world, if we can even call it that, is saturated with distinctions that human eyes could never possibly make. This raises a question we want to simply leave hanging in the air for now, like a soft cloud drifting across the ceiling as you sink deeper into your pillow. If colour is constructed by the nervous system, and different nervous systems construct different versions of the same world, which of these versions is the real one? Is the cold, colourless universe out there the true reality? Or does the rich, vivid experience your brain builds every single second possess a reality all its own? There is an even deeper layer to this conversation, and it concerns the origin of all this energy that the eye captures and the brain processes. The light must originate somewhere. The sun must shine. The photons must exist. The electromagnetic waves must carry enough energy to traverse space and still be capable of triggering a response from your cones. Where does this energy come from? This primordial force that animates the entire spectacle? The question simply hangs there. It does not need an answer right now. It only needs space to exist while your body sinks a little deeper and your breathing slows down all on its own. There is a star 93 million miles away that has no idea you exist. It holds no intentions, has no preferred direction, and harbours no special affection for the little blue planet orbiting it. It simply burns. It burns with a violence so absurd, so far beyond human scale, that any attempt to describe it in everyday terms immediately feels inadequate. And yet it is precisely this disinterested, brutal burning that makes the most delicate experience you know possible, seeing a colour. Think about how a camping stove works. You have compressed gas, a spark, and suddenly a flame. The flame does not create energy out of nothing. It releases energy that was already trapped within the chemical bonds of the fuel. The gas held potential energy, silent and waiting. The flame is merely the doorway that energy uses to escape. The sun operates in an analogous way, but the fuel is different. The doorway is different, and the sheer volume of energy released defies any calibration the direct human experience could provide. In the core of the sun, where the pressure is so immense it dwarfs anything terrestrial physics can produce in a lab, hydrogen atoms are forced so close together that their individual identities dissolve. 2 hydrogen nuclei fuse to form a helium nucleus, but the resulting helium nucleus weighs slightly less than the sum of the 2 hydrogens that birthed it. This missing weight was not lost, it was converted, and the equation describing this conversion is the most famous in all of physics, the one Einstein penned at the dawn of the 20th century. Energy equals mass times the speed of light squared. The speed of light squared is such an astronomically large number that even a minuscule fraction of converted mass results in an amount of energy that overflows all human intuition. The sun converts roughly 4 million tons of mass into pure energy every single second. Not 4 million tons of burned fuel like in a combustion engine. 4 million tons of matter that simply cease to exist as matter and begin to exist as radiant energy. This is happening right now as you hear these words. It happened the second before, it will happen the next. From this conversion emerge photons, the elementary particles of light. A photon has no resting mass. It weighs absolutely nothing, yet it carries energy, and the amount of energy it carries dictates what it will be capable of doing when it encounters matter. High-energy photons are gamma rays and X-rays, capable of penetrating tissue and ionizing molecules. Intermediate energy photons form ultraviolet light, which darkens skin and damages DNA. Slightly lower energy photons form visible light, that narrow slice of the spectrum that the eyes of terrestrial vertebrates learn to capture over hundreds of millions of years of evolution. And even lower energy photons form infrared, microwaves, and radio waves. What distinguishes these photons from one another is not a difference in substance. A photon of red light and a photon of a gamma ray are made of the exact same stuff, obey the same laws and travel at the same speed in a vacuum. What separates them is wavelength, frequency, and the energy each one carries, and this is where colour begins, long before any eye ever existed to see it. James Clerk Maxwell was a 19th century Scottish physicist who possessed the rare gift of seeing patterns where others only saw isolated phenomena. In his era, electricity and magnetism were studied separately, as if they were distinct forces of nature. Maxwell realized they were the exact same thing viewed from different angles. He gathered Faraday's observations on electric and magnetic fields, added his own mathematical intuition regarding how varying electric currents could create varying magnetic fields, and arrived at a system of equations that describe both in a unified manner. When Maxwell calculated the speed at which disturbances in this electromagnetic field would propagate, he found a number he immediately recognized. It was the speed of light. Light, he realized, was not merely illumination. It was an electromagnetic wave, an oscillation of electric and magnetic fields perpendicular to one another, propagating through space at the maximum velocity the universe allows. And if visible light was an electromagnetic wave, then there must be other electromagnetic waves of different lengths, invisible to the human eye but equally real. Maxwell's equations remain to this day one of the most elegant constructions in all of physics. They describe how electric fields generate varying magnetic fields, how varying magnetic fields generate electric fields, and how this mutual dance can sustain itself and propagate through space without needing any material medium to lean on. Light crosses the vacuum of space not because it travels inside something, but because it carries the very medium of its propagation within itself. This is a fundamental imbalance, and it is the imbalance that makes the visible universe possible. Think about how a wave in water behaves. The surface of the water is in equilibrium, When you toss in a stone, you create a local imbalance. A point on the surface rises higher than it should. This excess pushes the neighbouring water up, which in turn pushes the next water, and thus the disturbance propagates. The wave is not the water moving from one side to the other. It is the imbalance propagating. Light works in a similar fashion but without the water. An electric field varying in time creates a magnetic field varying in space. That magnetic field varying in space creates an electric field varying in time, and so on, indefinitely, each field feeding the other, the disturbance propagating without ever dissipating in the perfect vacuum. What Maxwell discovered is that the universe itself has an internal tendency to propagate this kind of imbalance, that this tendency has a precise speed, and that this speed is the speed of light. About 40 years after Maxwell, a young clerk at the patent office in Bern named Albert Einstein asked the question that would change everything. What would happen if you travelled alongside a photon? If you moved at the exact speed of light, what would you see? Maxwell stated that light was a wave moving at a specific speed. But speed relative to what? Newtonian physics dictated that velocities simply add up. If a train moves at 100 km per hour, and you throw a ball forward at 10 km per hour inside that train, the ball moves at 110 km per hour relative to the ground. By that same logic, if you move at nearly the speed of light and emit a photon forward, the photon should move even faster relative to a stationary observer, but experiments showed otherwise. The speed of light was always the same, entirely independent of the motion of the source or the observer. Einstein accepted this result as absolute truth and asked what the universe would have to be like for this to be possible. The answer was the theory of special relativity, and it required abandoning the notion that time and space are absolute. If the speed of a light is constant for all observers, then time and space must adjust differently for each observer. Time passes more slowly for those moving faster. Space contracts in the direction of motion. Two people in relative motion will disagree on when and where events occur. All of this because of light. All of this because the universe possesses this fundamental constant, this speed limit that nothing can surpass, and which light achieves precisely because it has no mass. But let us return to the core of the Sun, because that is where the story truly begins. The photons generated in the nuclear fusion of the solar core do not reach you with the speed of a bullet. The core of the Sun is so dense that a newly created photon can take anywhere from 10,000 to 100,000 years to journey from the core to the surface. It travels a few meters, is absorbed by an ion, re-emitted in a different direction, absorbed again, re-emitted again, in a random, tortuous path that physicists call a random walk. The photon that illuminated your face this morning might have originally been emitted in the Sun's core before the first anatomically modern humans even existed. When the photon finally escapes the solar surface, the photosphere, it enters space, and there its speed changes completely. In the vacuum of interplanetary space, it traverses 93 million miles in roughly 8 minutes. It crosses the void without being absorbed, without interacting with anything, until it encounters something it can interact with. It could be the moon, it could be an asteroid, it could be the Earth's atmosphere, it could be the leaf of a tree, it could be the retina of your eye. Each of these surfaces will interact with the photon in a different way, and this difference is dictated by the electronic structure of the atoms comprising each surface. An electron in an atom can only exist at certain energy levels, not at others. It is as if, instead of a ladder with rungs at any position, you had a ladder with rungs at very specific positions and absolutely no rungs in between. An electron can jump from one rung to another, but only if it absorbs the exact amount of energy corresponding to the difference between those two rungs. Not a fraction more, not a fraction less. This means that each type of atom absorbs very specific frequencies of light and reflects or lets the others pass. The green pigment in leaves, chlorophyll, predominantly absorbs the frequencies of red and blue light and reflects the green. Not because it decided to be green, not because it wants to look green, but because the specific electronic structure of the chlorophyll molecules has energy rungs that perfectly match the frequencies of red and blue and do not match the frequency of green. The leaf is green because the universe has rigid quantum rules regarding which photons can be absorbed by which molecular structures. Max Planck was the physicist who discovered, at the turn of the 20th century, that energy is not continuous. Before Planck, classical physics assumed that energy could take on any value, that it was possible to have half a unit of energy or a quarter or any imaginable fraction. Planck was trying to solve a technical problem regarding how hot objects radiate light, the so-called black body problem, and classical physics was yielding absurd answers. He tried, almost as a mathematical trick without believing it was real, assuming that energy could only be emitted in discrete packets, in whole integer amounts of a fundamental unit he called a quantum. It worked. The equations perfectly described the experimental data. Planck was deeply disturbed by his own discovery. He hoped someone would find a more conventional explanation. Einstein took the idea seriously, used it to explain the photoelectric effect in 1905, and the quantum went from a mathematical trick to the very foundation of reality. Light is not just a wave. It is also a particle. It is a photon, and each photon carries a discrete specific amount of energy determined by its frequency. It is this quantization that explains why colours exist as a physical phenomenon before they exist as an experience. The frequencies of visible light are not arbitrary. They correspond to a band of the electromagnetic spectrum where photons have enough energy to excite the pigment molecules in the cones of the human eye, but not so much energy that they cause direct damage to the tissue. Evolution tuned the sensitivity of our eyes to the window of frequencies that the sun emits most intensely and that the Earth's atmosphere transmits most efficiently. Our eyes are instruments calibrated to the specific sun we have, orbiting a medium-sized yellow dwarf star at a specific distance with a specific atmosphere. A creature evolved around a cooler red dwarf star, which emits primarily in the infrared, would have eyes calibrated to frequencies we will never see. Its version of what we call colour would be radically different, not because the physics was different, but because the receiving instrument was shaped by a different energy source. Colour does not begin in the eye, it begins in the star. And here is the mechanism in its most elemental stage. A specific photon with a specific frequency and a specific energy strikes a pigment molecule in a cone of the retina. The electron inside that molecule absorbs the photon, jumps to a higher energy level, and the molecule changes shape. Just one molecule, just one photon, a microscopic chemical shift in a microscopic receptor at the back of your eye. What happens when this process repeats not dozens, not hundreds, but millions of times per second, across millions of different receptors, all sending signals simultaneously to a brain trying to construct a coherent image of the world? Millions of signals arriving at the exact same time. That is the problem the brain must solve every fraction of a second that the eyes are open. It is not a simple problem of adding inputs and calculating an average. It is a problem of organization, of finding patterns amidst the noise, of building something coherent out of something that, in its raw form, is pure electrochemical chaos. And the way the brain solves this problem reveals something profound about the nature of color, something that goes far beyond any cone or pigment molecule. The signal leaving the retina has already passed through a first layer of processing before it even exits the eye. The bipolar cells and ganglion cells of the retina do not merely transmit what the cones detect, they compare. A typical ganglion cell responds to the contrast between what is in the center of its receptive field and what is on the periphery of that same field. If a point of light illuminates the center, the cell fires. If that same point illuminates only the edge, the cell goes silent. This system, which neuroscientists call center-surround organization, is the first piece of a difference detection architecture that will repeat itself on increasingly larger scales throughout the entire visual pathway. Difference is what matters, not the absolute value of a light frequency, but the contrast between adjacent frequencies in space and time. This sounds technical, but it carries a massive philosophical consequence. It means that the colour you perceive on an object is not determined solely by the light that object reflects. It is determined by the relationship between that light and all the light surrounding it. Place a grey square on a white background and it will appear darker than it is. Place the exact same square on a black background and it will appear lighter. The square has not changed. The light reaching your eye from it is identical in both cases. What changed was the context, and the brain processes context, not absolute values. This phenomenon, known as simultaneous contrast, was systematically documented by the French chemist Michel-Eugène Chevreul in the early 19th century. Chevreul worked in a tapestry factory and noticed clients complaining that certain black threads looked greyish when placed next to coloured threads. He investigated and discovered that the threads were perfectly black when examined in isolation. The problem was not in the dye, it was in the eye, or rather in what the eye does with what it receives. Chevreul spent decades documenting how adjacent colours influence one another, how an orange seems more vibrant next to a blue, how a yellow seems cooler next to a red. He was, without knowing it, mapping the rules of difference processing that occur in the retina and visual cortex. What Chevreul observed on the scale of a tapestry, neurologists later found on the scale of neural circuits. The cells that process colour in the primary visual cortex, the area of the brain that receives the first signal from the eyes, are organised in columns. Columns of cells preferring different colours alternate in space, like the elements of a microscopic mosaic. When light of a certain frequency falls on a certain region of the retina, a specific set of these columns is activated. But the active columns do not process information in isolation. They inhibit neighbouring columns that prefer opposite frequencies. Red inhibits green, blue inhibits yellow. This lateral inhibition is the neural mechanism of colour contrast, the exact same contrast Chevreul had observed in tapestries more than a century before anyone had the faintest idea how the visual cortex worked. Colour opponency, as this system is called, was formally described by the German physiologist Ewald Hering in the late 19th century. Hering observed that certain combinations of colours seem simply impossible to imagine. You can imagine a bluish-green, a reddish-orange, a yellowish-green. But can you imagine a reddish-green, a colour that is simultaneously red and green without being brown or grey? Can you imagine a yellowish-blue, not a green, but something that is simultaneously yellow and blue? The answer, for almost all humans with normal colour vision, is no. These combinations do not exist as possible perceptual experiences. Hering argued that this indicated red and green and yellow and blue were opposites processed by the same channel, so that maximum activation of one implies maximum suppression of the other. Hering's insight was considered speculative for decades, until the tools of modern neurophysiology allowed researchers to directly record the activity of individual cells in the lateral geniculate nucleus, the relay station in the thalamus through which visual signals pass on their way to the cortex. Russell de Valois and his colleagues, working in the mid-20th century, demonstrated that cells in this region exhibit exactly the pattern Hering had predicted. Some cells increase their firing rate in response to red light and decrease it in response to green light. Others do the opposite. Some respond positively to yellow and negatively to blue. Opponency was not speculation. It was anatomy. It was the way the neurons were wired to each other. This architecture of opponency solves a problem that seems simple, but is profoundly complicated. When you look at a red object on a sunny afternoon, and then look at the same object on a cloudy afternoon, the spectral composition of the light it reflects changes enormously. Direct sunlight is richer in shorter frequencies. The diffuse light of an overcast sky is cooler, and yet the object looks red in both situations. This ability to recognize the color of an object regardless of changes in illumination is called color constancy, and it is one of the most impressive feats of the visual system. Edwin Land, the inventor of the Polaroid camera, dedicated decades of his life to understanding color constancy. In the 1960s and 70s, he conducted a series of experiments that completely challenged the prevailing theories on color perception. Land projected the same scene using only 2 projectors with different colour filters, often just one red and one white, and asked observers to describe what they saw. Classical theory predicted that with only 2 wavelengths present in the image, people should only see variations of pink and red. Instead, they reported seeing a scene with rich colours, including blues, greens and yellows that were in no way present in the light reaching their eyes. Land concluded that the visual system does not process the colour of each point in a scene independently. It calculates the colour of each point relative to the average of the entire scene, using relative values instead of absolute ones. The brain is constantly estimating what the predominant illumination of the environment is and subtracting that estimate from each point in the image before calculating the resulting colour. Land called this process the Retinex theory, a term he coined to capture the idea that the processing happened simultaneously in the retina and the cortex, a distributed process with no single location. The genius of this system is that it is emergent. No individual neuron is calculating the average illumination of the scene. No isolated cell is doing the subtraction that produces constancy. This calculation arises from the interaction of millions of cells, each doing something very simple, comparing what is in the centre of its receptive field with what is on the periphery. And from the collective result of these simple comparisons emerges a sophisticated global behaviour. It is the same principle that allows an ant colony to find the shortest path between the nest and a food source, without any individual ant having the slightest concept of an optimal path. This emergence is not specific to colour. It is a general principle of how the nervous system works. But colour is perhaps the most accessible example because it is visible, because you can look at a tapestry or a grey square on different backgrounds and see with your own eyes the result of processing happening in your tissues without you having any conscious access to it. The colour you experience is not the raw signal reaching your eyes. It is the solution to a system of equations your brain solves continuously. Equations that take into account not just the light present, but the expected light, the light of yesterday, the memory of how familiar objects usually look under familiar illuminations. This memory has a location in the brain. The visual cortex is not a homogeneous region. It is divided into areas with specialized functions, and researchers like Miyazaki, working in the late 20th century, contributed to mapping this division with increasing precision. A specific area, identified in brain imaging studies and in cases of patients with localized brain lesions, seems to play a central role in calculating color as a perceptual constant. Patients with damage to this area can lose color constancy while retaining the ability to detect differences in brightness and shape. They see the world not as a collection of objects with colors, but as a collection of surfaces with spectral values that change with every variation in lighting, like a camera without automatic white balance. The geometry of the visual field also leaves deep marks on the organization of the cortex. The retina is not uniform. In the center, in the fovea, the density of cones is extremely high, allowing the fine resolution needed for tasks like reading or recognizing faces. In the periphery, the density drops rapidly and rods take over. This geometry is preserved and amplified in the cortex. The representation of the fovea occupies a disproportionate area of the primary visual cortex, much larger than would be expected by the physical size of the fovea in the retina. This cortical magnification means that a huge fraction of your brain's visual processing power is dedicated to the small central point of the visual field where details are resolved with the greatest precision. But color resolution in the fovea is not simply higher, it is qualitatively different. The fovea contains mainly long and medium frequency cones, those that detect the bands we call red and green. Short frequency cones, those that detect the blue band, are rare in the fovea and absent in its exact center. This means that pure blues in the center of the visual field are calculated by a different mechanism than blues in the periphery, and means that color acuity for short wavelengths is intrinsically lower than for longer wavelengths. You can verify this yourself by looking at text written in bright blue on a white background from a certain distance. The edge of the blue text will look slightly blurry even when red text of the same font and size is perfectly sharp. The uneven distribution of cone types, the opponency architecture, the columnar organization of the cortex, the magnification of the fovea, the temporal integration that allows color constancy. All of this constitutes a global structure whose individual components do not seem, when looked at in isolation, capable of producing the final result. Each cone responds to a frequency. Each ganglion cell compares center and periphery. Each cortical column prefers a direction of opponency. And from the sum of these local operations, all simple, all mechanical, arises the subjective experience of color, with all its richness, with all its capacity to evoke emotions and memories, with all its indecipherable beauty. This architecture, elegant and robust as it is, operates within a certain envelope of conditions. It assumes a certain range of luminances, a certain speed of lighting change, a certain predictability of the environment. And when an element enters the scene that alters these conditions dramatically and unexpectedly, the structure we just described, no matter how sophisticated, begins to reveal its seams, its limits, the points where the elegance of the solution found by evolution over millions of years encounters something it was not prepared for. The element that alters these conditions dramatically does not come from outside the visual system. It is not a brighter light or a more saturated color. It is, of all possible things, the temporary absence of light followed by its return. It is the transition, the interval, the change of state. The amplifier that the visual system encounters with the most difficulty is not the intensity of a stimulus, but the speed at which the luminous context transforms around the observer. When you step from a very dark environment into a very bright one, or when a cloud moves away and sunlight floods a field that was in twilight, the system we described in previous parts needs to recalibrate the entirety of its operations in fractions of a second. The cones need to adjust their sensitivity. The ganglion cells need to redefine what they consider the center and periphery of illumination. The color opponent cells need to find new balance points between red and green, between blue and yellow, and all this happens simultaneously, in parallel layers, without consciousness being able to pause the experience while the processing reorganizes. It is in this simultaneous reorganization that the amplifier acts, because during the transition period, while the system has not yet found its new equilibrium, the colors you perceive do not correspond precisely to the frequencies reaching the retina. They correspond to the previous state of the system applied to the new stimulus. It is as if an entire orchestra needed to change key during the performance of a piece without pausing a single measure. The instruments that adjust faster create dissonances with those still in the old key. The result is neither silence nor pure noise, but something in between, an imperfect, revealing harmony. This process of chromatic adaptation is powerful precisely because it seems invisible. Most of the time, the system manages to make the transition fast enough that consciousness does not register the discontinuity. You enter a room with yellowish lighting, and after a few minutes a sheet of white paper still looks white, even though the wavelength it reflects is mathematically very different from the white light of the sun. This happens because the system recalibrated. It learned in the minutes of exposure that this is the dominant illumination of the environment, and adjusted all its references from it. This phenomenon has a specific name, color constancy, and it is one of the most elegant and invisible operations the brain performs continuously. Color constancy is an amplifier because it operates on a paradox. To keep it functional, the system needs to deliberately ignore real information reaching the retina. It needs to literally discount the spectrum of the ambient illumination before calculating what it considers to be the true color of an object. This discount is an estimate, and estimates make mistakes. And when they do, the mistakes are not small measurable deviations only visible in a lab. They are radically different experiences of the same physical object by different people, or by the same eye under different conditions. The most famous case of this discounting error became known as the dress. On a day in February 2015, a photograph of a dress circulated the internet and divided the world between people who saw the fabric as blue and black and people who saw it as white and gold. The image was slightly overexposed with ambiguous lighting that allowed each person's visual system to apply a different discount. Those who interpreted the lighting as artificial and yellowish discounted the yellow and saw blue and black. Those who interpreted the lighting as natural and bluish discounted the blue and saw white and gold. The dispute was so fervent it seemed impossible, because each group was absolutely certain they were seeing reality. Both were. Different realities, produced by different discounting systems, activated by internal context no one consciously chose. The dress was not an internet curiosity. It was a rare moment when the invisible amplifier became visible to tens of millions of people simultaneously. And what made the moment unsettling was not the ambiguity of the photograph, but the certainty each observer felt. No one thought they were in doubt. No one felt their perception was a hypothesis. The colour seemed as definitive as the temperature of their own body. This sense of certainty is part of the mechanism. The subjective experience of colour does not come accompanied by a footnote saying it is an interpretation. It arrives as a brute fact, as primary data, as if the colour were in the object and not in the interaction between object, light and nervous system. And this is necessary for the system to work. An animal that perceived every colour as a provisional estimate revisable at every instant would not be able to make quick decisions based on colour. Perceptual certainty is functional, but it has a cost, which is precisely the impossibility of perceiving, without specific training, that what you see is a construction. Colour constancy does not operate alone. It works in conjunction with a broader process scientists call chromatic adaptation, which can be divided into at least 3 phases with different temporal dynamics. The first phase is practically instantaneous, occurring in milliseconds. The photoreceptors adjust their sensitivity to the present light level. The second phase takes a few seconds to a few minutes. The ganglion cells and colour opponency mechanisms recalibrate their balance points. The third phase is the longest and most interesting, potentially taking many minutes or even hours in extreme conditions. It is the cognitive perceptual process by which the brain learns to interpret the relationships between surfaces in the new environment. This third phase is where the amplifier acts most strongly, because it is influenced by expectations, memories and cultural context. The exact same wavelength you associate with the colour of a ripe banana will be perceived as yellow even under lighting conditions that should make it ambiguous, because the system brings to perception the information it already has about what bananas are. This is so robust that there is a documented effect called colour memory, where objects with semantically associated colours like the sky, grass, blood are consistently perceived as slightly more saturated and closer to their canonical colour than they actually are under the present illumination. Colour memory is an amplifier because it causes past experience to modify present perception non-consciously. You literally see what you expected to see, not as an illusion or deception, but as the normal operation of a system that uses all available information, including what came from the past, to construct the most useful representation of the environment. The paradox is that this mechanism, which makes vision more efficient, also makes it less faithful in a photographic sense. But vision was never photographic. It was always interpretive. The observable manifestations of this amplification process are numerous and distributed throughout everyday experience in ways we rarely recognize for what they are. The simplest and most universally experienced is the chromatic afterimage. When you stare fixedly at a saturated colour for about 30 seconds and then look away at a white surface, you see the complementary colour hovering in space. Looked at a bright red dot and you will see a cyan dot. Looked at an intense green field and you will see a field of soft magenta. This phenomenon is not a superficial optical curiosity. It is the direct, visible evidence of the colour opponency system at work. What happens during those 30 seconds of fixation is that the cones sensitive to the red frequency become progressively fatigued. They respond less and less to the stimulus. When the gaze shifts to white, which contains all frequencies, the fatigued cones contribute less to the total signal, and the result is that the system interprets the white light as if it were lacking red, producing the experience of the complementary. The afterimage is not on the wall, it is not in the light. It is in the momentary state of imbalance of the processing system, projected onto the world as if it were part of it. You can do this right now, or the next time you're in a room with a well-lit coloured surface. Fix your gaze without blinking for half a minute and then quickly move your eyes to the ceiling or a light wall. The ghost that appears is the clearest signal in existence that the colour you see when looking normally at things is also, to some extent, a state of your system, not a property of the object. A second manifestation, less obvious but extraordinarily revealing, is simultaneous colour contrast. Place a small grey square on a red background and it will look slightly greenish. Place the physically identical grey square on a green background and it will look slightly reddish. The square has not changed. The light it reflects has not changed. What changed was the surrounding context, and the opponency system responded to the context by adjusting the representation of the centre. This occurs because the system does not process isolated points. It processes relationships, differences, edges, contrasts. And a grey in relation to a red is a different thing than a grey in relation to a green, not just mathematically, but perceptually, experientially. Simultaneous colour contrast was described with scientific precision by the French chemist Michel-Eugène Chevreul in the early 19th century while working in a tapestry factory. He noticed weavers complaining that certain grey threads seemed to have a strange tint when placed next to coloured threads. After careful investigation, Chevreul realised the problem was not in the threads, but in perception. He published his findings in a book that became a reference for painters, especially the Impressionists and Pointillists, who began using the phenomenon deliberately to create visual vibrations on their canvases without mixing pigments. Georges Seurat was perhaps the artist who took Chevreul's understanding furthest in pictorial terms. Instead of mixing paint on the palette, he applied dots of pure colour to the canvas, letting the observer's visual system perform the mixing. What he called divisionism and critics dubbed pointillism was, in essence, a conscious and methodical exploration of the fact that colour exists in the brain, not on the surface. He was building instructions for the perceptual system, not images for passive eyes. A third manifestation, which belongs to a different category because it involves movement, is the watercolour effect, when a thin line of saturated colour is drawn on a surface and that line is bordered by a darker line. The colour seems to diffuse into the interior of the delimited area, even if that area is completely white. The surface looks tinted, watercoloured, even though no paint was applied there. What happens is that the perceptual filling-in system, which normally fills uniform regions based on the edges it detects, receives the signal from the coloured line as an edge with chrominance, and extrapolates that chrominance into the interior of the region with reduced intensity. This filling in is not a bug. It is the same operation that makes you perceive surfaces as having a uniform colour even when the illumination on them is gradient, even when parts are in shadow. The system inferred from edges and context what the surface must be, and filled the internal representation with that inference. Most of what you see as the colour of a large surface is inference, not direct point-by-point measurement. If you have ever noticed that certain colour combinations seem to vibrate or pulse, even in static images, what you experienced was another manifestation of the same system. The artist Joseph Albers dedicated decades to studying these interactions, documented in his book Interaction of Colour, where he demonstrated that the same colour can look radically different depending solely on the colours around it. Not slightly different, not noticeably different, radically different to the point of seeming like an entirely different colour. He called this the relativity of colour, and what relativity demonstrates is that colour is not an absolute property of a surface, but a relational value the brain calculates as a function of the entire available visual context. The system that performs all these operations, colour constancy, simultaneous contrast, perceptual filling in, colour memory, is robust insofar as it works well in the vast majority of environments that existed when it evolved. Environments illuminated by the sun, by fire, by open sky, by water reflections. All of them have certain spectral regularities that the system learned to use as premises. Solar illumination has a peak in the spectrum the system knows. Natural surfaces have reflectance distributions that obey certain statistical regularities. The system built its discounting and constancy heuristics on top of these regularities, and that is why it is, at the same time, robust and fragile. Robust because within the envelope it was built for, it functions with extraordinary precision and stability. Fragile because outside that envelope, when it encounters illuminations that do not follow expected regularities, when it encounters surfaces whose reflectance properties violate expectations, when it encounters context providing contradictory clues, the system does not make a rougher estimate. It makes the estimate its rules produce, even if that estimate is radically wrong regarding the physics of the environment. This specific fragility is what makes the amplifier so interesting. It does not destroy the system. It reveals the seams, and every time you see a color illusion, every time you experience an afterimage, every time two physically identical squares look like they have different colors because they are on different backgrounds, you're observing in real time the evidence that what you experience as the reality of color is a partially autonomous construction of your nervous system, functioning with incomplete data, solving an impossible problem in the best way it found over millions of years of trial, error, selection, and refinement. And this system, no matter how elegantly and reliably it works most of the time, lives in an equilibrium that is not static. It is dynamic, continuous, sensitive to perturbations that can come from unexpected directions. The environment it was built for is gradually disappearing, replaced by technologically created environments, with light spectra that never existed in nature, with screens that emit light instead of reflecting it, with surfaces combining synthetic pigments in ways no natural environment ever produced. The system responds to this new environment with the same tools it always used, and the seams that appear when it meets this new environment are revealing in ways we are only just beginning to understand. The seams appear first at the edges, not in the central regions of perception, where the system operates with more confidence and more data, but in the peripheries, at the thresholds, in the transition zones where one category begins to yield space to another. It is in these border territories that the dynamic equilibrium of chromatic construction reveals its most vulnerable nature, its dependence on conditions that must remain within certain limits for the illusion to sustain itself with its usual elegance. The system that constructs colour is not robust in the sense of being insensitive to perturbations. It is robust in the sense of being resilient within a range, capable of continuously adjusting to fluctuations that remain within the parameters it was calibrated for. But this range has edges, and when conditions push against these edges hard enough, or push from directions evolution never anticipated, the system enters a different mode. A mode where the mechanisms that normally operate invisibly and harmoniously become visible precisely because they begin to fail, to oscillate, to produce results that do not correspond to what would be expected from a system functioning within its normal parameters. Think about what happens when illumination falls below a certain threshold. During the day, under abundant light, cones completely dominate chromatic perception. They operate in parallel, the three types sending signals the cortex interprets and integrates, to produce the chromatic richness of daytime visual experience. But as light diminishes, cones need more photons to fire, and a point is reached where they simply do not receive enough stimulus to maintain their contribution. Rods, which function well with very dim light but are insensitive to wavelength variation, begin to dominate, and the world loses colour in a way that is not abrupt but gradual, a fading that happens first in the peripheral regions of the visual field and advances toward the centre as darkness deepens. At this threshold, the two systems coexist for a period. Cones still contribute some signal, rods already contribute their own signal, and the cortex receives a mixture that does not fit perfectly into any of the categories it learned to process. The result is a degraded, unstable chromatic perception, where colours seem to have lost saturation without having completely lost their identity. A dark red becomes something the system still recognises as belonging to the red family, but without the vividness, without the presence that defined it under full light. It is like hearing a familiar word spoken by an altered voice. So altered the word is barely recognisable, yet still recognised. This threshold between photopic and scotopic vision is just one of the transition points where chromatic construction reveals its internal mechanics. There are others, less related to light intensity and more related to the nature of the stimulus or the conditions of the system processing it. And some of these transition points produce phenomena that are not just interesting as curiosities, but reveal fundamental aspects of perceptual architecture that would otherwise remain completely hidden. Chromatic adaptation, which under normal conditions operates so fluidly it is imperceptible, can be forced to reveal its mechanics when subjected to extreme conditions. If an observer is exposed to an intense saturated colour field for a prolonged time, the opponency mechanisms processing that chromatic category begin to adjust. The neurons responding to red, for example, gradually reduce their sensitivity after prolonged stimulation, while the neurons responding to green, in opposition, maintain their relative sensitivity. When the red stimulus is removed and replaced by a neutral field, the imbalance left in the opponency system manifests as a perception of green where objectively there is no green at all. The chromatic afterimage is not a flaw, not a system error. It is direct evidence that the colour perceived corresponds to nothing in the stimulus, but is entirely a construction based on the relative state of the comparison mechanisms. These adaptation phenomena can be intensified to the point of producing experiences that seem completely dissociated from the physical reality of the environment. There are specific chromatic illusions where a static pattern produces the perception of movement and pulsation, where regions of the visual field receiving exactly the same photon pattern are perceived as having completely different colours, where the chromatic identity of a surface seems to change dramatically depending on which other surface is next to it. Each of these phenomena, no matter how dramatic it seems, is simply the system doing exactly what it always does, operating with the same contrast, comparison, and normalization mechanisms, just applied to situations where these mechanisms produce results that conspicuously diverge from what would be expected from a direct correspondence between stimulus and perception. Adelson's checkerboard illusion, for example, shows two squares on a perspective checkerboard. One is in the illuminated part of the board, the other is in the shadow cast by an object. The two squares reflect exactly the same amount of light, the same spectrum, the same photons reach the eye from both, and yet one is perceived as dark grey, and the other as light grey, so different it seems impossible they are identical. The system interpreted the context, inferred that one is in shadow, and therefore must be intrinsically lighter than it appears, and adjusted perception accordingly. Even when knowing the two squares are identical, even after verifying with instruments, even after covering the rest of the pattern to eliminate context, the perception persists. Knowledge does not undo the construction. The system that builds perception has no access to the knowledge the conscious mind developed about its own operation. This reveals something profound about the nature of instability in the system. Instability is not simply a state of confusion or failure. It is frequently a state of genuine ambiguity, where the stimulus is compatible with more than one interpretation, and the system oscillates between them or chooses one, and holds it with a firmness that resists conscious revision. The famous dress that divided the internet into two camps with absolutely opposite certainties about whether it was blue and black or white and gold was not a perception error. It was an extreme case of chromatic ambiguity where the system needed to decide how to interpret the colour of the illumination present in the scene, and depending on that decision, the object's colours changed dramatically. Each person who saw the dress was seeing correctly, given the set of assumptions their system had adopted about the illumination. The divergence was not in the dress, It was in the different starting points, different systems adopted to resolve the ambiguity. What makes these phenomena so revealing is precisely that they expose the structure of assumptions that normally operates completely invisibly. The system assumes things about the nature of illumination, about surface properties, about spatial relationships between objects, and uses these assumptions to resolve the ambiguity present in every visual stimulus. When the assumptions work, when the environment is the type they were calibrated for, the construction is so smooth and consistent it seems to simply be reality being passively received. When assumptions encounter ambiguous situations or artificially constructed scenarios designed to subvert them, the system enters a mode where its constructive nature is exposed. Humanity began observing and cataloguing these phenomena systematically, a little over 2 centuries ago, although scattered observations on chromatic illusions and hallucinations exist in much older texts. What changed with modern science was the ability to measure, to isolate variables, to create controlled stimuli allowing specific hypotheses about underlying mechanisms to be tested. A psychophysicist in a lab can create a visual field where every parameter is known with precision, where the intensity and spectrum of every point in the stimulus are controlled, and then accurately record what the observer reports perceiving. The discrepancy between the measured physical stimulus and the reported experience is precisely the space where construction becomes visible and studyable. Modern neuroimaging techniques have completely transformed this project. With functional magnetic resonance imaging, it is possible to observe which regions of the visual cortex activate in response to different chromatic stimuli, and how these activations change when context changes. It is possible to see, literally, how the same photon pattern produces different neural activation patterns depending on the context it appears in. It is possible to track how information flows from primary processing areas to higher order areas, where decisions about chromatic identity seem to be made, and how this flow is modulated by information arriving top-down, from higher order regions back to primary ones. This bidirectional flow is crucial for understanding why dramatic phenomena persist even when known to be illusions. The contextual information producing the illusion does not enter the system, only after basic processing, as a later correction. It modulates basic processing itself, altering how signals are amplified or suppressed before they even reach consciousness. Color perception is not a serial process starting at photoreceptors and ending in consciousness, with each step depending only on the previous one. It is a massively parallel bidirectional process where expectations and context influence processing at very early stages of the chain. This means the dynamic structures the system generates in intense mode are not simply errors occurring on the surface of an otherwise correct process. They are the result of the same process functioning the same way, with the same rules, applied to conditions that expose the architecture in a way normal conditions do not. And these structures, once generated, have a persistence extending beyond the moment the triggering stimulus is present. The afterimage persists for seconds after the original stimulus is removed. Chromatic adaptation can last minutes. In some cases, like certain forms of chromatic hallucination associated with altered states of consciousness or specific neurological conditions, the structures the system generates can persist for much longer periods, functioning as a sort of parallel chromatic reality, overlapping the perception of the physical environment. While you rest, somewhere, someone is sitting before a panel of precisely calibrated instruments, recording how an observer responds to 2 color fields that physics says are identical, and perception says are completely different. Somewhere, a visual cortex is being scanned while processing an ambiguous stimulus, and in the images appearing on the researcher's screen, it is possible to see the regions competing, the networks oscillating between 2 interpretations before committing to one. Somewhere, someone experiences for the first time that illusion, where a static pattern begins to pulse with a life of its own that does not exist on the screen, and wonders with a mixture of awe and disorientation what exactly is happening between their eyes and their experience. What these observations collectively reveal is that dramatic phenomena are not exceptions to the system's normal functioning. They are amplifications of it. They are situations where mechanisms operating smoothly and invisibly under normal conditions are pushed into a regime where their operation becomes visible, where seams appear, where the constructive nature of chromatic experience ceases to be a theoretical hypothesis and becomes an immediate, undeniable experience. And what becomes even more intriguing as these phenomena are studied in more detail is that they do not seem to happen in isolation. There are patterns of co-occurrence, connections between categories of experience suggesting the system constructing colour is intertwined with other systems in a way far beyond what would be necessary to simply identify light wavelength. There is a convergence neuroscientists took decades to fully comprehend, and which even today remains more of a map than a fully explored territory. The system constructing colour in the brain does not operate as an isolated module, like a sealed chamber dedicated exclusively to processing wavelengths. It operates as a node in a network, and the main partner in this network, the one it exchanges the most information with, the one it is most deeply intertwined with, is the system constructing memory. Not memory in the sense of conscious recollection, not the ability to recall the sky was blue on a specific childhood afternoon, memory in the most fundamental primitive sense. The nervous system's ability to maintain implicit records on what it encountered before, to calibrate expectations based on accumulated exposure, to learn what things tend to be before deciding what they are. This exchange does not happen as a consultation, as if the colour system paused and asked the memory system what to expect. It happens continuously, in parallel, so integrated that trying to separate it analytically is like trying to separate wetness from water. The projections descending from the higher visual cortex to the early stages of chromatic processing carry contextual information already filtered by learned expectations. When you look at an orange, the signal reaching your retina is processed before it even becomes conscious perception by a set of preparations including what your system knows about how oranges usually appear under different lighting conditions. This preparation is not retrieved as a memory. It is embedded in the very architecture of how processing happens. Functional neuroimaging studies mapping these connections revealed something particularly intriguing about the anatomy of this intertwining. The regions responding most intensely when someone sees a specific colour are the same regions showing partial activation when someone merely thinks about that colour, or reads the word naming it, or is in a context where that colour would be expected. The distinction between perceiving and anticipating at the level of neural architecture is much less clear than our conscious experience would lead us to suppose. The system seeing blue and the system expecting blue share substrate. They use the same circuits, just in different activation regimes. This creates a feedback loop with a disturbing elegance when examined closely. What you perceive today influences the expectations shaping what you will perceive tomorrow. Every chromatic experience is not just an isolated datum passively recorded. It is an update to a model that will then influence all future chromatic experiences. This loop operates on multiple temporal scales simultaneously, and understanding how it behaves on each reveals different, equally fascinating aspects of its nature. In the short term, the loop manifests as adaptation. In a matter of minutes or even seconds, the system recalibrates in response to what it encountered. You enter a room lit by orange light, and initially everything seems slightly orange. Within minutes, the chromatic appearance of objects in the room normalizes. Your color perception system calculated the dominant illumination and subtracted its contribution, allowing the relative chromatic properties of objects to appear more clearly. This process of chromatic adaptation happens continuously, adjusting the system's zero in response to the immediate environment. It is a constant calibration operating below the threshold of consciousness, maintaining the stability of chromatic appearance through variations that, if literally recorded by photoreceptors, would produce completely different images. But the loop also operates on longer timescales. Over weeks and months, the system accumulates exposure to specific chromatic environments and adjusts to them in ways going beyond simple contrast adaptation. People living in environments with distinct dominant color palettes, whether for geographic, cultural, or occupational reasons, develop baseline calibrations differing subtly from those of people in other environments. These differences are not illusions or errors. They are adjustments of a system whose goal is not to record absolute wavelengths, but to extract useful information about the world from available light patterns. What constitutes an optimal adjustment depends on the environment where the adjustment occurs. On the scale of decades, the loop manifests in ways touching something much more personal. A person's chromatic experience is not static over a lifetime. Aging produces progressive changes in the eye's lens, which becomes progressively yellower, selectively filtering shorter wavelengths. An elderly person is literally seeing the world through a filter a young person does not have, and yet within the subjective experience of a continuous life, these changes are rarely perceived as changes. The system recalibrates so gradually that the appearance of the world remains subjectively stable, even while the physics of what is reaching the retina transforms. What you see now, with your eyes at this moment, is not what you will see decades hence, and yet there will be a continuity of experience making the two perspectives indistinguishable from the inside. On the scale of centuries, the loop reveals itself through something only visible when looking at historical and archaeological records of how different cultures categorized and named the colors they perceived. There are surprisingly consistent patterns in how chromatic categories emerge in different languages over time. Cultures having only two basic color terms usually distinguish between light and dark. When a third term emerges, it is almost invariably for red. When a fourth appears, it tends to be for yellow or green. When a fifth for the other between yellow and green. When a sixth for blue. This sequence has been documented in hundreds of studied languages, and its consistency suggests it is not arbitrary, that it reflects something about the structure of the perceptual system preceding culture, that there is an order in which distinctions become salient determined by biology before being shaped by history. What these historical patterns reveal about the feedback loop between perception and cultural memory is that language does not merely describe chromatic categories existing before it. It consolidates them, makes them sharper, allows them to be transmitted precisely across generations and between individuals. A culture with a specific word for a chromatic distinction trains its members to perceive that distinction more consistently and easily. The linguistic category feeds back into the perceptual system, tuning its sensitivity precisely where the culture collectively established a distinction matters. The loop between perceiving and naming, between individual experience and collective convention, operates across generations in a way gradually shaping the distribution of how color space is inhabited within a community. On the scale of millions of years, the loop manifests as evolution. The current architecture of the human visual system is the product of a very long history of gradual adjustments in response to environmental pressures we can no longer directly observe. Early mammals were primarily nocturnal, and their visual systems were optimized to detect movement and shape in low-light conditions, not to discriminate color. Primates evolving in tropical forest environments gradually developed the ability to distinguish wavelengths with more resolution, possibly as an adaptation to identify ripe fruits against green foliage backgrounds. The trichromatic vision most humans possess today, with photoreceptors sensitive to 3 distinct regions of the spectrum, is an evolved solution to a specific problem the environment posed. But here, sensitivity to initial conditions becomes especially apparent. The trichromatic vision we have is not the only possible solution to this problem. Some bird species have 4 types of photoreceptors, including one sensitive to ultraviolet, and probably inhabit a space of chromatic appearance radically different from ours. A small percentage of human females have 4 functional types of photoreceptors, and there is evidence these tetrachromats can distinguish between stimuli appearing identical to most people. The space of chromatic appearance we inhabit is not the space of chromatic appearance. It is a space of chromatic appearance determined by the specific details of the architecture evolution built along a particular historical path. These limits reveal themselves with special clarity when we try to predict how the system will behave under conditions outside its evolutionary experience. Artificial illumination with a very narrow spectrum, like certain sodium lamps emitting essentially a single frequency, produces chromatic appearances the system lacks adequate mechanisms to process stably. Objects appearing to have distinct colours under sunlight reveal themselves to be indistinguishable under this illumination, not because their physical properties changed, but because the system normally inferring colour from reflectance patterns lacks enough information to complete the calculation. Colour constancy, that elegant ability to keep chromatic appearance stable through lighting changes, depends on having enough information about the illumination spectrum to subtract it. Reduce that information to zero, and the system simply has nothing to lean on. This points to a fundamental limit that is not technical but conceptual. The system constructing colour is an inference system operating well within the conditions it was adjusted for, but whose behaviour under radically different conditions is not predictable from its general principles. You can completely understand how the system works and still be unable to predict how it will behave when faced with a sufficiently novel situation. This sensitivity to initial conditions, this dependence on specific historical and environmental context, is not a system flaw. It is a characteristic of any system that learned to operate efficiently within a specific niche. Adjustment to the niche is simultaneously the source of competence and the limit of reach. There is a particular beauty in contemplating such a system that is simultaneously extraordinarily sophisticated and fundamentally dependent on assumptions it cannot verify itself, that produces remarkably stable, reliable results within its operating range and collapses in revealing ways when that range is exceeded. That has a history of hundreds of millions of years and operates at a speed making that history completely invisible to its user. That seems simple from the inside as immediate undeniable experience and reveals disconcerting depths when examined from the outside. The sensation of contemplating this system from a sufficiently distant perspective is something like what you feel when looking at an intricate mechanism and realizing every piece you can see is connected to other pieces you have not yet seen, and that the connections between them follow a logic beginning to feel familiar without ever becoming completely familiar. You recognize patterns, you perceive there is coherence here, that things are not random, that there is something organizing them, and at the same time you realize the something organizing them is deeper than any description you have managed to formulate so far. What makes this system simultaneously comprehensible and surprising is precisely this balance between order and openness. It has rules clear enough for us to study it, model it, predict its behavior under many conditions with considerable precision, and at the same time it has connections deep enough with other systems, a history long enough, a sensitivity to conditions subtle enough, that every answer we manage to formulate about it opens space for 3 questions we had not yet thought to ask. When you allow yourself to rest in this contemplation, when you stop trying to solve the system and begin merely perceiving its texture, something curious happens. The complexity that seemed to demand effort begins to feel less like a problem and more like a landscape. A vast landscape with depths not revealing themselves all at once, with patterns repeating at different scales, with a coherence you feel more than you can articulate. And within this landscape, very quiet, very much at the centre, there is something you begin to realize has not yet been named on this journey, something perhaps simpler than everything described so far, and which might be precisely what makes everything else possible. There is something at the centre of all this resisting naming, not because it is obscure, but because it is so fundamental words reach it and slip away, like fingers trying to hold water. You have passed through many layers on this journey. You saw how light travels through space without colour, how the eye captures wavelengths without ever seeing hues, how the visual cortex constructs what you call red from firing differences between cells that never knew something called red existed. You saw colour is not in the object, not in the light, not in the optic nerve, And now, right here, right in this place of near dreaming, it is possible to name what has not yet been said with all the clarity it deserves. Colour is a feedback loop, not just a construction, not just an illusion, not just an interpretation. It is a system feeding on itself, correcting itself as it advances, learning as it perceives. And understanding this as feedback completely changes how the phenomenon can be contemplated. Think about what happens when you enter a dark room after being in bright light. For a few moments you see almost nothing. Then slowly shapes begin to emerge. What is happening is not simply your eyes adjusting to the lack of light. What is happening is the entire colour processing system recalibrating its reference points. The cones, responding to specific wavelengths, become temporarily saturated by intense exposure and then recover sensitivity gradually and differentially. The brain, perceiving the arriving signals are weaker, begins selectively amplifying them. It is a negative feedback loop, a process stabilizing perception by automatically compensating for changes in lighting conditions. But there is also the opposite loop, positive feedback, the one amplifying instead of stabilizing. When you fix your gaze on a colored point long enough and then look at a white surface, you see the complementary color floating before you. This happens because the cones responding to the original stimulus became temporarily depleted, while the others remained with sensitivity intact. The result is a color existing nowhere except in the internal dynamics of your visual system. It is the system amplifying an imbalance until it becomes visible as experience. These two types of feedback, the one stabilizing and the one amplifying, exist simultaneously throughout the entire color perception process. And the system's elegance lies precisely in how they balance. If there were only stabilization, you would never perceive subtle nuances, small tonal differences would go unnoticed. If there were only amplification, every small light variation would explode into distorted, unusable perceptions. What exists is a dance between the two, a constant negotiation between sensitivity and stability, between openness to the world and internal coherence. The molecular dimension of this is even more dizzying when you descend into it calmly enough to let the details settle. Every cone in your eye contains proteins called opsins, folded in very specific ways, coiled into three-dimensional structures, creating small chambers where a very particular molecule can fit. This molecule is called retinal, and it is derived from vitamin A. In darkness, retinal sits in a specific configuration, folded in a certain shape. When a photon of light strikes it, something remarkable happens. Retinal changes shape in less than a picosecond, which is a trillionth of a second, perhaps the fastest chemical reaction known in biological systems. This shape change is the event triggering everything. The opsin, sensing retinal change configuration, activates a signaling cascade, eventually opening ion channels in the cell membrane, eventually generating the electrical potential travelling down the optic nerve, eventually reaching the visual cortex, eventually resulting in what you call seeing red. The entire experience of colour begins with a single molecule folding differently because a packet of energy struck it. It is almost impossible not to fall silent before this. And there is one more molecular layer rarely mentioned. The opsins of the three cone types, those responding to short, medium and long wavelengths, are structurally very similar proteins. They evolved from a single ancestral protein through duplications and gradual mutations over hundreds of millions of years. This means the trichromatic vision you possess, this ability to perceive the world in all that richness of hues, arose from small molecular changes accumulated over time so long the mind cannot truly embrace it. The colour you see today was sculpted by a molecular history beginning long before eyes existed to see anything. Viewed as an integrated system, colour perception reveals a property complex systems scientists call robustness. The system works even when many of its parts are operating imperfectly. Colourblind people still perceive a rich, coherent world, just with a different palette. People with damage to specific parts of the visual cortex lose very precise aspects of chromatic perception, while keeping others completely intact. The system has redundancies, alternative pathways, compensation mechanisms activating when others fail. This is not accidental. It is an emergent property of a system shaped by billions of years of selective pressure in an environment where visual perception mattered for survival. A fragile system, collapsing completely with any perturbation, would have been discarded long ago. What remained is a system maintaining its essential function even under adverse conditions, adapting, compensating, finding alternative paths when main ones are blocked. An emergence, that mysterious property by which complex patterns arise from simple rules, is at the heart of the entire colour experience. Every cone in your eye follows a very simple rule, respond more or less strongly depending on the wavelength striking it. Every neuron in subsequent visual processing layers follows equally simple rules: sum inputs, subtract inputs, fire when a threshold is reached. There is no instruction in any of these simple rules saying, construct the experience of seeing blue. There is nowhere in the system written, when these conditions are met, produce the sensation of deep turquoise at dusk. And yet, from this cascade of simple rules, precisely this emerges: the experience of blue, the sensation of turquoise, the specific, unmistakable quality of how red differs from orange in a way you immediately recognize but cannot describe with words other than other colors. Emergence is the point where scientific explanation meets its limit and mystery begins, not a mystery of ignorance, but a structural mystery, something that might be the case even after all possible science is done. Deep down, color is simply the way consciousness touches the world. This is the synthesis. Not a reduction diminishing the phenomenon, but a simplification revealing it. Every element contemplated on this journey converges on this central idea, with a naturalness seeming inevitable when you see it. The light travelling through space without colour is the world existing on its own, indifferent, complete in its physics. The eye-capturing wavelengths is the point of contact, the interface where world and consciousness begin to meet. The cells comparing signals are the process by which this encounter becomes information. The cortex constructing representations is where information becomes experience, and the experience of colour, that irreducible subjective quality of seeing red, is the touch itself. Consciousness touching the world, not passively, not simply receiving what is already there, but actively, constructively, creatively. Consciousness does not find colour in the world. Consciousness brings colour to the world, and in doing so, it is not distorting reality or creating illusion. It is doing the only kind of contact with reality possible for any conscious system, transforming the world into experience, translating what exists into something that can be felt. Every person seeing a sunset and feeling something before those hues is participating in this touch. Every child learning the sky is blue, and then spending the rest of their life with that information integrated into their perception, is carrying an example of this process. Every artist spending decades studying how colours interact on canvas is deepening their understanding of how consciousness constructs the chromatic world. All of them, unknowingly, are practicing the same phenomenon this journey tried to illuminate. And you, now, after all this, will never see a colour the same way again. Not necessarily because you will think of photoreceptors and opsins every time you look at the sky, but because there is now, even if silently, even if only in the texture of your perception and not in your explicit thoughts, an awareness that what you see is not simply what is there. It is something you are doing, something you are creating in the act of perceiving, and this creation is an act of beauty, not deception. Beauty. The system begins to rest now. You can feel it. The questions arising throughout this journey do not need to be answered tonight. They can settle softly, like leaves on water, without sinking, without making waves, just resting on the surface. The colours of the day are dissolving. The reds and oranges and yellows your cortex constructed over all the hours since you woke are slowly unravelling, like ink in warm water. Chromatic processing, always so active, so tireless, begins to loosen its pace. In the darkness of the room, there is less and less work for the cones to do. You are safe. Right here, right now, you are completely safe. The universe existing without colour continues existing, tranquil and indifferent in its physics. Wavelengths continue travelling through space. Photons continue being emitted by stars that never knew something called blue existed, and that is fine. There is a deep peace in knowing the world continues its work while you rest from yours. While you rest, the eyes of other creatures continue building their versions of the chromatic world. Somewhere, a bee navigates a garden seeing ultraviolet patterns on flowers that to you seem simply yellow. Somewhere, an octopus adjusts its chromatophores to mimic a surface it perceives in a way no scientist yet fully understands. Somewhere, a bird uses light polarization to orient itself on a flight lasting thousands of miles. The universe takes care of you. This is not a sentimental metaphor, it is a description. The same physical laws keeping electrons in the orbits of atoms comprising every cell of your body are the same laws governing the light your eyes will capture tomorrow, and your brain will transform into colour. You are part of the same system generating stars and dissolving galaxies. There is a continuity between what you are and what the universe is that no perceptual separation can undo. Everything is in order. The retinal molecules in your cones, which during the day folded and unfolded hundreds of millions of times in response to light, are now in relative rest. The signalling cascade converting light into experience is quiet. The visual cortex, which during waking hours processed an amount of chromatic information defying any comparison, is slowing its activity to the slower rhythm of sleep. While you rest, colour continues existing in every awake mind in the world. In every eye still open at this moment, wavelengths are being compared, differences calculated, experiences constructed. The phenomenon inhabiting this journey does not sleep. But you can. You are part of this. You always were. Every colour you ever saw was a moment the universe folded back on itself in a way complex enough for matter to experience matter. Every red, every blue, every nameless hue you noticed in the sky on a specific dusk you probably barely remember now was an instant consciousness touched the world and transformed it into something that could be felt. You were the place where these touches happened. You were the space where the universe learned its own colours. This is a very quiet and very large thing to carry, and you do not need to carry it actively tonight. You can simply let it settle. The breath deepens a little. The eyes, even closed, relax the imperceptible effort the muscles around them always maintain during wakefulness. The mind, which for so long navigated waves and photoreceptors and cortex and molecules and philosophy, begins to loosen its narrative structure. You're going to a place where there is no colour processing because there is no light to process. A place of darkness much deeper than any dark room, quieter than any starless night. Sleep is the place where consciousness stops touching the world for a while and rests within itself. And this too is part of the cycle. The day builds colours. The night dissolves them. The day returns and builds them again. You wake tomorrow with all chromatic machinery ready to begin anew, to capture the first wavelengths of morning and transform them into the specific experience of how dawn light looks different from midday light, how the same room has a different chromatic quality depending on what time of daylight enters the window. But that is tomorrow. Now there is only quietude. Now there is only rest. Now there is only you, and the gentle darkness, and the silence needing no colour to be complete. The universe continues its silent dance, and we rest in its embrace. Thank you for walking with me tonight. Sleep well.